Alright guys, so before this point we have seen some stuff where we're given square roots, different radicals, and we had to simplify whatever was going on under the radical. What we're going to be doing now is we're going to be graphing square root functions. Just the square roots, we're not getting to cube roots or anything like that until later. So starting off with just the original, we call them the parent function for the square root graph, we're going to write down just all of the information that there is to know, take a look at what the original graph should look like, and then we'll figure out how to transform them, just like we do with a bunch of other graphs we've worked with. So the parent function is this. We've got f of x equals the square root of x. Just plain and simple, just an x under the square root, and remember this is always our function notation. So the domain, this is the first time, and I think I've told you guys this was coming. Before, the domain was always all reals. We could plug in any value of x that we want. But with the domain this time, with square root functions, it's not actually all reals because this stuff under the square root has to be positive. So what you do to find the domain is you take whatever you see under the square root, which here it's just an x, and you make sure that it is always greater than or equal to 0. So that's how you figure out what your domain is. So again, you take whatever is under the square root and make sure it's always going to be greater than or equal to 0. Can't be less than 0 because then we'd have a negative under the square root. We'd have imaginary numbers. We don't know how to graph imaginary numbers. We get ourselves into a whole mess. And then the range is whatever you get when you plug in these different values. So our range is strictly positive y values as well. And I'll kind of explain that more once we see the graph in front of us. All right, X-Intercepts. This crosses right through the origin. So we've got x equals 0 is the x-intercept, and then y equals 0 is the y-intercept. Again, that'll make more sense once the graph is in front of you. It's not defined for negative x values. We're not allowed to plug in any negative x values. So the graph just kind of stops when you look at the left-hand side of the x-axis. All right, and then end behavior, we've seen this in the past. As x approaches 0, our function approaches 0, so it just heads right to the origin, 0, 0. You'll see that with the graph in front of you. And then as x approaches positive infinity, f of x also approaches positive infinity. X doesn't ever approach negative infinity because we can't use negative values. So here's what the graph looks like. Got our big coordinate system here. It starts right at the origin, and then if you picture plugging in some different values, say you plug in 1, the square root of 1 is 1. It's like that would be a point right there. We don't know the square root of 2. We don't know the square root of 3. We know the square root of 4 is 2. So we could plot a point right there. So what this thing does is it curves and it doesn't grow very quickly at all. So we've got points like this. The next point it would hit would be 3, 9. So it's a very, very slow increase. But it does increase, and actually it increases forever, which is why we say as x goes off to the right, f does increase forever. So we'd go to 9, 3, and then 16, 4. This is the inverse of an x squared function. All right, so all these pieces here, the intercepts for this particular one, they both go right through the origin. You can see that because I'm only plugging in positive values of x, I'm only getting out positive values of y. And different things will change on the next page when we start to transform. So let's start just by identifying the domain and range of this first function. Remember I told you right here, you take whatever is under the square root and make sure it's positive. So we take just this piece right here that's under the square root, and we're going to make sure it's positive. So take that expression and say that it needs to be greater than or equal to 0. So we're going to do what we need to do to get x by itself. So all that is would be adding 2 to both sides. Okay, so as long as x is greater than or equal to 2, this function will be defined. All right, so we start with that. You get the x value because it only includes values that would be non-negative. All right, so we said it's strictly greater than 0. So this is my domain. And then for the range, what you do is you plug this lowest y value, the lowest x value in to see what your lowest y value would be. So we do f of 2, plug that in, we get square root of, so now I'm plugging the 2 in for x. And I come up with 0. So that means that my lowest y value is 0, so it could be anything higher than that. So my range, y could be anything greater than or equal to 0. And that's exactly what we had up here. So there's no shift happening yet. That is happening on the next page. Okay, so that's just a quick domain and range. If we look on the next page, we're going to talk about all our different transformations. Okay, so we can go up, down, left, right. Notice this is remarkably similar to the standard form for a parabola. Okay, so reminder, let's say, recall for a parabola, we had a, and then the only difference was this was in a squared function instead of a square root function. But other than that, all these pieces are exactly the same. So in a parabola, the vertex was hk, and then a told us all about whether we stretched, compressed, things like that, flipped upside down. So this is actually going to be identical. We don't call it a vertex with a square root function, but we can just say that it's the starting point. All right, so like this would be your starting point, and then the graph goes from there. All right, so horizontal translation, left and right all has to do with h. So whatever the value of h is, that'll tell you your translation. It will move h units right if you see the square root of x minus h. Remember, it's always the opposite. And it will move h units left if you see x plus h. So remember, the left-right movement is always opposite of what you think it's going to do. Vertical translation has to do with k. It does exactly what it looks like it's going to do. We could either go k units up, and that is if you have a plus k on the end, or we could go k units down, and that's with a minus k on the end. All right, so let's... Okay, and then orientation and shape, that all comes from the A. Remember, the A tells you two different things. So if A is less than 0, the graph gets flipped upside down. If A is positive, it stays right side up, so I'm not even going to write that down. And then if its value is greater than 1, that's a vertical stretch. These are the same rules that we've seen for a bunch of different types of graphs. And if A is a fraction between 0 and 1, there is a vertical compression. Okay, so these are almost identical to the rules that we had for the parabola over there. So I just wrote this just to kind of compare for you. So let's graph these functions right here, talk about what each one of them is doing. So for part A, your starting point is the opposite of this, comma, this. All right, so our starting point is at positive 4, positive 2, and then we have a stretch by a factor of 3. Okay, so I will show you exactly what that looks like. So let's set up a little coordinate system here. Our starting point is 4, 2. So there's 4 up to 2. So remember, according to our translations, this moved 4 units to the right. So I moved 4 units over here. And then this tells me I move 2 units up. So I move up here. That's my starting point. And then the 3 is going to be a vertical stretch. All right, so it stretches 3 units up. So remember, we can almost use that like a slope. All right, so from this point, I can go up 3 units and then over to the right 1. All right, so I can go up 3, over to the right 1, just to see one more point, and then sketch, and it just looks kind of like that. Sorry, I'm running into my words there. So that is what your function would look like. Remember, this is my starting point, so I can actually use that starting point to come up with my domain and range. So my domain and range, my starting x value is 4. I don't have anything to the left of that. So my x values have to be strictly greater than or equal to 4. It starts at 4 and then it goes to the right, so that means greater than or equal to. And then for my range, let's see, my starting y value is 2, and then it just goes up from there. So in terms of y, up means greater than or equal to, and my starting value is 2. So these two numbers right here will always match these two numbers right here. All right, so your domain and your range would be these positive values of x bigger than 4, and then values of y bigger than 2. All right, let's look at the second one. My starting point, I take the opposite of this for x, so that's negative 5, and then I take this number for y, so that's negative 6. And then what that negative on the outside is going to do is it's going to flip it upside down. Okay, so just to give you an idea of what we're looking at. So if we start here, We need to be over in negative territory. So I go over to negative 5, down to negative 6. So that's my starting point right there. And then what I do is I flip upside down. Okay, so instead of going up and curving to the right like this, I'm actually going to go down and curve to the right. But remember, I can use this negative 1 to plot another point. So I can use the negative 1 to go down 1 to the right 1 and plot another point there. So then I can curve like this. And that would be my upside down square root function. Okay, so domain and range. Domain and range, my starting x value is negative 5, and I go to the right, which means greater than. And then the starting value of my range is negative 6, but I go down. So this time the range is actually less than or equal to, because I start at the negative 6 and I go down. And in terms of y, down would be less than, up would be greater than. All right, so let's sneak this last one in real quick, and your second video will be a very short one. So we've got this whole background information about an object spinning with centripetal acceleration. We get this function right here. That relates the velocity to the acceleration. So first we want to graph the function. All right, so graphing the function, the only thing that we have transforming is 2. So we can actually, this is going to seem like a strange little rewrite, but we can pull the square root of 2 out and separate it from the square root of a. So then this becomes our vertical stretch right here. Okay, so it's not moving up, down, left, or right. It's just starting at the origin. Okay, so since there's no, plus or minus in here, there's no plus or minus on the outside, it starts at the origin, 0, 0. And then there is a stretch by a factor of the square root of 2. And the square root of 2, if you plugged it in, comes out to be about 1.4. Okay, so our graph will look like this. We start at the origin, right here, and then we stretch by a factor of 1.4. So go up and over. So we're going to go up about 1.4 and then over 1. Okay, so my graph will look like that. Okay, and then it says, what would be the centripetal acceleration with a velocity of 4 meters per second? So what I'm going to do is, they say velocity is 4. I'm going to plug that in right here and then solve for a. So 4 equals square root of 2a. I'm going to do whatever I need to do to get that a by itself. So what that involves first is squaring both sides, like that. So when I square the 4, I get 16. When I square the square root, they cancel out, and I just have the 2a. And then my next step would be to divide both sides by 2. So I just have this a left, because my 2's will cancel, and 16 divided by 2 of course leaves me with 8. All right, and so if any of you guys are physics people, the acceleration is meters per second squared. So you can write it like that. So that would be my final answer.